welcome to another video on Boolean Algebra. I'm going to start off this video by doing the example we finished off with in our last class, and then I'm going to go forward, do a few more gates. I don't expect that this video will be too long actually, but I want to get into detail about how these gates work. Now again, the whole idea behind Boolean Algebra is to determine if an output is going to be on or off. That's the entire thing. And if you relate it to computers, it's the idea that you need a few conditions to be true before you execute a program. For example, you can check if x is 1 and y is 7. If both of those things are true, if x is 1 and y is 7, then you can run a certain part of your code, for example. Or if it's not true, do some other thing. It's just basic flowcharts. We'll get to that a little later, I think. But for now, let's deal with the problem at hand, which is solving this circuit. So we have a couple problems when we start this. And again, we did this at the end of last class, but this is what it turned into. And so I want to recap in a clear, organized way. First of all, we have inputs A and B. I'll call this one A and I'll call this one B. Currently in this chart, in this diagram I should say, it's 0 and 1, but it could be any combination. Usually we start with both on, one off, 1 off, 1 on, and both off. Or call it ones, call it zeros, call it true, call it false, call it on, off. It doesn't matter, they all mean the same thing. And then we need to look at our gates. Our first gate here, the triangle with a little nib on the end, a little circle, which I call the not dot. That's our not gate. So this gate is called not gate. And if A is going into it, then the output of this gate is going to be not A. So that's one of the outputs that we're going to need to keep track of. If we look at the other gate, we see that it's coming from B. It's going into this gate. We can see that A is going into this gate. So there's something to do with A and B here. We just need to know what the combination is. And it turns out that this is an AND gate. And in Boolean has the symbol of a multiply, a dot. Okay? So not, also known as complement, looks like this. And looks like a dot, but the dot kind of doesn't make a lot of sense on its own. So normally you see with A and B together, but it is just the dot. So just to be clear, and means our dot, not is something with a line on top, okay? It's hard to write, just the line, and so usually we put the letter underneath it. Anyway, what's my point? My point is we need to figure out what this is. It turns out it's going to be not A and B. If the input coming in, this input, which is not A, if that is 1 and the input B is 1, then this light will turn on. So just by looking at the circuit, look at this. This is 0 right now. We follow this 0. It's off, off, off. It goes through the NOT gate, and it suddenly turns on. All right, that turns on. So as it turns on, we have a 1 going through here. That's a 1 currently. From the other side, the B, that's 1, which means the circuit is on. So we travel along this. It's already blue, but I wanted to make a point. We have 1 and 1 going in. 1 times 1 is what gives us our 1. So the circuit is still on, and then in this case our light bulb lights up, or we get a 1, or whatever way you want to put it. So let's look at our truth table. Our final result we care about is not A times B. That part's actually really easy, but I'm trying to make a lot of connections at the same time. First things first, I didn't mean to write that not on top. First things first, let's fill out our not A table. This part here. Not A. Well, if A is 1, not A is 0. If it's not 1, it's 0. There's only 2 options. Same thing again for the next row. It's got to be 0. If it's not 0, then it's going to be 1. And same thing for the next row. So our not A column is complete, but the only reason we got the not A column is to compare it or do an AND operation with the B column. So, for example, some students find it useful to call this Step 1, call this column 2, which means we can do 1 multiplied by 2. So whatever way works for you, at the end of the day, we're doing not A and B. So in this case, I'll just do the notes. This would technically be our not A, which is 0, multiplied by 1, because it's not A times B. But we don't write that because that would mess up our table. It would become a little bit too unwieldy, so we call it 0. All right? Hopefully that's starting to make some sort of sense. I'll keep track of what it was. It was actually 0 times 1 is where that came from. Let's do not A times B again. Not A times B, 0 times 0 is 0. So 0 times 0, or 0 and 0, is 0. We only get 1 out of an AND gate if both inputs are 1. In this case, that's where we're going to get it in this case, okay? So 1 times 1 gives 1, and that should be no surprise. Anything times 0 is 0, so it's got to both be 1. And finally, 1 times 0 is 0. So long story short, for AND gates, if it's multiply, they got to be 1. If they're not 1, they're going to be 0. Let's do this one. Let's see if we can figure out what's going on here. This is input A, this is input B. This gate here is an OR gate. An OR gate is actually a plus. So it's like addition, which means it's going to take the first input. What's that? Well, this is coming from A, so the first input must be A. And the second input, what's it going to be? Well, it starts off as B, but it goes through a NOT gate. So if it's a NOT B, if B goes in and it turns into a NOT B, then we must call it NOT B. So that will then carry through on this wire. I guess I could draw over it. This comes through. NOT B goes into the OR gate. So at the end of the day here we have A or NOT B. That's how we draw these circuits. And then we figure out what this is. If it satisfies the rule, in this case if one or the other is 1 or on, the final answer will be on. So let's fill out our table. 1, 1, 0, 0, 1, 0, 1, 0. That's just a really simple way to try to take care of all of our possible results. And in the end, we're going to need A plus not B, but we can't get A plus not B until we know what not B is. So we normally do that first. And that's just a matter of getting the complete opposite of the B column. 0, 1, 0, 1. Once again, it's just literally taking the B column and doing the complete opposite operation. 1's turned to 0, 0 turns to 1. Now we have A or not B. So it's literally A or not B. You just compare them to each other and add them. So you add those two columns together. 1 plus 0 is 1. 1 plus 1 is still 1. 0 plus 0 is 0. 0 plus 1 is 1. So this came from 1 plus 0, 1 plus 1, 0 plus 0, 0 plus 1. Remember, please, please, please remember that plus means or. So we can think about this in a totally different way and it will still be correct. If A or not B is on, then the answer is on. So we just say, as long as one or the other is on, we get our answer 1, okay? In this case, we have 2 switches on, so the final answer is on. In the third case, we don't have a 1, so one or the other needs to be 1. It's not, so it's off. In this case, not B is on, so our final answer is on. Hopefully it's starting to become more clear to you. If it's not, I've got a whole book full of examples that we can go through on this. There's no shortage of examples. It's just a matter of if you need them or not. So let's move on to page 23. Let's look at this one here. So in this case, we have something that looks different. We have a 0 and we have a switch that's on. All that means is a 1. But in general, all we care about is A and B. Actually, before I move on to this, I should double check this answer here. Back in this case, an important connection to make, I think, is 1. If A is 1 and B is 1, this should be on. So in this case, if A is 1 and B is 1, the final answer should be on. So in fact, we are actually checking our work by going back to the truth table and comparing it to our original graphic. Let's do that with 5 as well, visually. If A is 0, so one of those two, and B is 1, so A is 0 and B is 1, our light bulb will be on. So it's 1. And so our truth tables, which is what these tables are called, these truth tables are just telling us one possible combination of all the possible combinations. It's a living thing. If you build this circuit like I've shown you before, you can turn things on, you can turn things off, you can see what the results are going to be. As it should be. If you have two different switches in real life, you start flicking the switches around, you're going to get different results. Okay, let's do this one. This is an AND gate. This is a NOT gate. So I'm going to take these, move them in here, shrink it down, just so that we have something there. All right, actually, I'll write it underneath because I don't want you to have to write like a tiny, like an ant. All right, and a NOT. And what we have is A and B. So possible combinations, either they can both be on, they can both be off, or you have some combination in between. The first gate it goes into, we have A and B going into the AND gate. So A and B. What's the symbol for AND? The symbol for AND is a dot. It means multiply. So you've got AND means multiply. That's important, okay? I'll make them the same color. NOT means whatever you get from the previous, whatever is coming into the gate is turned into its complement or its opposite. So it means we have A and B, but it's the opposite. Whatever was coming in will now be flipped, which is why you can see this visually, okay? There is no signal coming into the gate. There's nothing coming through. It's not a blue wire right now. But when it comes out of the gate, it becomes a blue wire, which means there's now signal being sent through it, even though there wasn't signal coming into it. There's signal coming out. All right, let's try to make this table. So first we have A and B. That's all the possible combinations that can come into that first gate. So that's 1 times 1, or A and 1. Are they both 1? Yes. The rest of them are not both 1, so they're all 0. In the next case, we have the exact same column, but it's just not. So literally, you take what's here, you flip it, and it becomes its opposite. 0, 1, 1, 1. That's all you need to do. Right? Not 1 is 0. Not 0 is 1, and so on. That's all you need to do. This gate, this combination of gates, has a special name. An AND gate, followed by a NOT gate, is called a NAND gate. Not AND. AND followed by NOT, I should say NOT, is not AND. And it actually has a special look. It has a completely unique symbol. It's an AND gate with a little nib on the end. You see the NOT dot. That means not. And this whole gate is called NAND. So sometimes that symbol will come up. It's the exact same thing as not AND, but it's done at the same time. It's done in one big operation. But in this case, it was done in two steps. This case, if you look at this clearly, you can see a NOT following an OR. So this is actually called a NOR gate. So I'll just write that here just so it's out of the way. And there we go. And you can probably guess what the symbol is going to be. It's still this Star Trek looking thing, but it has our NOT dot. Means not, and then the whole thing, if we see it as a group, it's called NOR. But in this case, it's been split up into two pieces, so let's take a look and see what we got. So I've set up the two inputs. Let's see what we're going to get. In the first case, we have A and B, they're both going into an OR gate. I'll put that underneath just to keep consistent. It's A or B is allowed to go into this gate. That's what the gate takes. That's what it'll spit out. It'll spit out if either one is on, we'll just continue that way. So OR, 1 plus 1, 1 plus 0, 0 plus 1, 0. And notice, as long as one or the other is 1, you get 1. Now when they come in, it's not. So it takes A plus B, and it will inverse it. So same exact case as before. We had no signal coming in, and now we have signal coming out because it's done the opposite. The symbol for that, A or B, not. This is NOR. It's called NOR, not OR. So what it means is you can do the OR in your head, 1 or 1, okay, we get 1, and then do the opposite in your head, which is 0. So not 1, not 1, not 1, not 0. So once again, we just take the values directly and spit out what number we know needs to be true. So hopefully that makes sense. That's how we do these truth tables. I'm going to go back and check to see if my truth table is matching what I was given. So in this case up here, I have a 0. It's off. The switch is off. It's not blue. And a 0. Judging by my truth table, a 0 and a 0 as inputs should give a final output of 1. A 0 and a 0 as inputs give a final value of 1. So I'm okay. This is exactly what I wanted. We've confirmed one case. Same thing here. A 0 and a 1 is giving a final output of 1. A 0 and a 1 is giving a final output of 1. So at least we know our truth table is matching our diagram. That's very important because it's the exact same thing being done 2 different ways. Let's see what else we have. We have NAND and NOR. Okay, interesting. I just introduced those. Maybe this is some sort of foreshadowing at play. In the little tip box here, it says, notice the extra nib on the right side of the logic gates for NAND and NOR. This means there's a not involved. Not and not or. So let's see how she goes. Turns out, we'll see, we've actually done this question already, just in a different way. So we have A and B, 2 possible inputs A and B. This is called a not and gate, also known as NAND. We know it's not and because of the dot in front. All right, notice this means not. Okay, so it means that we have A and B, but not A and B. So if one and the other are both on, then we do the opposite. So remember, 1 and 1 normally gives 1, but we want not that, which would give a 0, okay? Or 1 and 1. If we have 1 and 1, that gives 0. 1 NAND 1, if it normally gives 0, it would have to give if it normally gives a 1, it would give a 0. So 1 times 1, let me show you the work. 1 times 1 is equal to 1, which must be equal to 0. So until you get good at this, you'll have to do this by hand and step by step, but eventually you can do it in your head. The next one, we have 1 and 0. So we have not 1 times 0, which is the same as not 0, which must be 1. The exact same case is true for the second step, so I don't need to do that again. And then we have not 0 times 0. Not 0 times 0 is not 0, which must give 1. So a NAND gate, once again, this is called NAND. A NAND gate takes and then flips it inside out. So normally, and is, I'll say output is 1 when both inputs are 1. So NAND, it means the output is 0 when both inputs are 1. because it's this very annoying opposite operation going on. So take some time to think about that, get some intuition for it, do some more practice later if you need to. But it turns out it's the exact same thing as an AND going into a NOT gate. We have 0, 1, 1, 1 for NAND. Don't you think that's why we have 0, 1, 1, 1 for the previous AND going into a NOT gate? Because they're completely related. So hopefully that makes a bit of sense to you. Let's double check our answer as we're here. We have a 0 and a 0 giving an answer of 1. 0 and 0 give an answer of 1. So it looks like we're okay. Let's try NOR. I know that this is NOR because it looks like an OR, but I see the NOT. So it's important to notice that. So we have A and B, both going into an OR gate, which would normally be A plus B, but it's NOR, so it has a NOT on top of A plus B. Not A or B. NOR. Not OR. I feel like I'm speaking another language here. 1, 1. 1, 0. 0, 1. 0, 0. As a side note, just while I'm thinking about it, these combinations, that's every possible combination of A and B. There are no other combinations. Some students like to just go at it in any order. They're like, all right, I got a 1, 1, I got a 0, 0, I can have a 0, 1, I guess, I can have a 1, 0, I guess. And they go with that. That's perfectly fine, but it's a real nightmare to mark. And generally speaking, there's only two ways that any sane Boolean algebra working person would represent these. They would either use 1, 1, 1, 0, 0, 1, 0, 0, or the complete opposite, which is actually more common, but in this course we do the opposite, would be 0, 0, 0, 1, 1, 0, 1, 1. Please choose one of those two methods. If you mix them all up, it's just going to be really annoying. It's going to take longer for marking, and you're just dealing with a non-standard way of doing it. Okay, so let's take a look at the note I made for AND. I said AND, output is 1, but both inputs are 1. So for OR, in this case, output is 1 when one or both of the inputs. Now again, we're talking about the output being 1. That's a normal OR. If it's not OR, it's this persnickety one. The output, well, let's do the table and see what happens. Outputs, what's it going to be, do you think? 1 or both of the inputs, or when one or both of the inputs are 1. So 1 or 1. 1 plus 1 is 1. Not that is 0. 1 plus 0. Not 1 plus 0. So not 1 is 0. Not 0 plus 1. Well, that's not 1, which is 0. And in this case, this is not 0 or 0, which turns into a 1. So in this case, the output, if either of the inputs are 1, the output is 0 when either of the inputs is 1. I recommend that you just remember how OR works and just flip the output. Because if you know how OR works and you flip the output, you'll be perfectly fine with this. So normally, for OR, 1 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. The NOR version of this flips everything. Right? It puts a NOT over all of this, which puts a NOT over all of this, which means the final answers are just the opposite of what we started with. So that's what NOR does. Finally, let's check. 1 and 1 gives us 0. 1 and 1 gives us 0. In other words, on and on gives an off, or whatever way you want to put it. All right, so now we've done NAND, we've done NOR, and hopefully it makes sense to you. So I've jumped ahead to the other page, page 25, just the next page, and I'm going to introduce this topic and I'm going to stop the video there because I'd rather do the rest of this stuff in another video or in class. But the last gate we're going to deal with is XOR, or exclusive OR. Just as a recap here, let me just remind you what we've dealt with so far. We've done AND, OR, NOT. We've added together NOT and AND to make a NAND. And we've combined OR with NOT to make a NOR. There is one last Boolean algebra gate or statement that we need to deal with, and that's XOR. So when I say that we have 6 things, we have AND, OR, NOT, NAND, NOR, and we also have XOR. We have 6 gates in total to be concerned with. Okay, let's see what exclusive OR means. Exclusive OR in Boolean algebra. Boolean exclusive OR. It has this crazy looking symbol, which I like quite a lot. I don't even know what it's called. I will just call it the XOR symbol. It does have a sort of name. It's an encircled plus sign. So it's a plus with a circle around it. Represents XOR. XOR, what it does, it's a special operator that only gives one, also known as true, if either but not both of its inputs are true. What does this mean? Well, we can see that if they're opposite, if the inputs are different from one another, it's actually going to give us our truth value. So this is what the XOR looks like. Notice, compare it to OR. OR looks like this. XOR, the only difference is a second bar underneath it. So it's very sneaky. It looks very similar. This is OR, this is NOR, or sorry, XOR. This is OR, this is XOR. I'm just confusing myself here. So, A or B. Let's look at this. A or B, but not both. So it gives a 1 if either but not both of its inputs are 1. So look at this. This is 1 and this is 1. So either but not both is 1. So this must be 0. We're allowed to have one or the other, but only one or the other, not both. In the second case, one or the other. Hey, that's great. We can take that. That gives a 1. In the second case, we have one or the other being 1, but not both. And in the last case, either but not both must be 1. Well, they're both 0, so this is a 0. So XOR is a weird one. XOR is definitely strange. Let me make a note here. XOR gives 1 when the inputs are different. So let me convince you of that. These inputs are the same. These inputs are the same. They give 0. So I'll say same, we get 0. Same, we get 0. But I don't need to write the zeros there. But the most important thing is they're different. I should probably make it more clear. These inputs are different, 1 and 0. These inputs, there's definitely a better way to write this, but I'm just doing my best to help you understand. These are 2 different inputs, which means they give a 1. So XOR gives 1 when the inputs are opposite or different, and so this is a explanation or a demonstration of that. Hopefully it makes some sort of sense. Let me try to make it clearer in one more way, and then we're going to finish. The way I'm going to show you is comparing it to a light switch in your house. So I wrote that there at the top. XOR is like a stairway light in your home. It's like the light that's in your stairwell that has 2 switches. Let me show you what I mean. So suppose this is your stairway light. And at some point along the way, both of these switches ended up being off. Let's see what happens when we turn these switches, click these switches around. Interesting. So it's doing something to this light. Let's try to get into the nitty-gritty about what it's doing to the light. This gate here, so in the middle, that is a XOR gate. It's exclusive OR, which means the output will be 1 when the inputs are different. But let's get a better intuition of this. Look what happens with the light. No matter what I click, it's going to turn this on and off. It will never stay off in 2 states back to back. Just watch this. It's now off. I'm going to click it. It's now on. Click, it's off. Click, it's on. Off. On. Off. It doesn't matter what I do. I can click one all day. I can jump to the other one, click it all day. It will just flick the light on and off. That's what it does. There is no possible way to get it to turn on back to back. As long as I'm changing a number, it's going to change this light. Well, that's exactly the kind of circuit you want in your house for a stairway light. You're at the bottom of the steps, okay? Just say you're at the bottom of your steps and the light is off. So you're at the bottom of the steps and you turn the light on and you walk up the stairs. You're at the top of the stairs. It's nighttime, so you're going to bed. You can't touch that bottom, the switch that was in the basement or in your first floor. You need to click on the other light at the top, and sometimes it'll be in the up position and sometimes it'll be in the down position. But it doesn't matter, because as long as it's different from the other one, or as long as the other one has been flicked, you see what I'm saying? It'll switch the light on. So once again, you're at the bottom, you're in the bottom of your first floor of your house. The light is on. Let's just say it's off, okay? The light in your stairwell is off. It's late at night, you want to go upstairs. You're in the bottom. Turn the light on. Walk up the stairs. Hey, the light's still on, but I should probably turn it off. Save the trees, let's go to bed. You click it on top. Even though they're both in the on position, the light is off. What makes that circuit possible is a logic gate called XOR. It's exclusive OR. So what we see here, this is exclusive OR. We have one or the other will be off. In fact, as long as they're different, it will be on. And it's difficult to understand it as a truth table. It's easy to understand it as a stairway light. So hopefully that can help you. If it doesn't help you, then forget about the stairway light and just know that XOR gives 1 when the inputs are different. Okay, so we didn't actually cover too many examples today, but I did a lot of explanation as to why these two truth tables work the way they do. We'll do lots more examples in our next class. I hope you have a great day. I hope you enjoyed the video. If you did, give a like and subscribe, ring the bell, and I'll see you soon. All the best.